So in the previous video, where we actually saw the single head self-attention, and then we actually drew the multi-head self-attention, we didn't have a chance to sort of discuss that a little bit more. So what we were trying to do today is to just, in this video, to just look at this kind of block diagram and trying to kind of to justify it. So first of all, we probably noticed something that given this kind of input tensor X, which is this kind of well-known matrix to us T by D, we can write that these heads, and as a reminder, heads was basically this kind of block diagram. Heads are working in parallel. And because of the fact that we need to now instantiate kind of multiple heads, we actually want to make sure that we do not increase linearly with the number of heads, the complexity. So the heads are working in parallel and with the computational complexity of the single head self-attention. So despite the fact that we have multiple heads, what we do is we take care of some of the dimensionalities of each single head self-attention. We divide it, let's say, by the number of heads, capital H, that is actually shown in this kind of a diagram, and so that the computational complexity is kind of manageable. And so we use the number of heads parameter, capital H, to reduce the dimensions of the tensors involved. So it's best to leave this kind of discussion at a later stage where we will see some actual implementation of this kind of approach, of this kind of transformer model in an actual large language model. It's a GPT-2 language model. And we will come back to this then. Just notational wise, we still have the sort of query projections and key projections. Just in many times we qualify this capital Q, capital K matrices and V with a specific small letter h, and the small letter h is the index of each kind of head. And what we are trying to do is to, with this kind of multiple heads, is to, look at exactly what kind of tokens are actually able to help me, let's say, across linguistic patterns. We will see, by the way, in computer vision that instead of linguistic patterns, this single head self-attention are attracting their sort of attention, if I may call it like this, into the different aspects of features. Like, for example, one head may be associated with, let's say, the texture information in an image. Another head may be attending to color, and another head may attending more to shapes. So in computer vision, things are a bit more, I will call it intuitive, but I just want you to sort of understand that from the natural language person perspective, just associate a head with, let's say, a linguistic kind of pattern. And then the next kind of discussion will actually be the dimensioning of this kind of multi-head self-attention. And as I said, the dimensioning, let's postpone the dimensioning when we look at sort of a Visual Studio Code implementation of an actual model. Let's look at GPT-2, which is a kind of a manageable model, and it's still kind of relevant towards this kind of studying the GPT kind of family of language models. Okay, so the next kind of a block that we should be concerned with is the block about the raw kind of compute stage. So if I may go a little bit to treat now this multi-head self-attention, now it's turn arrived to enclose this whole thing in a kind of a block, and I'll call this multi-head self-attention. What I will do now is I will take the take this x as a vector, as a tensor at the input, and I am going to pass it through what we call a layer normalization. We have seen to some degree earlier kind of batch normalization in another video. So what we will see here in this kind of layer normalization is a very similar kind of operation what we have seen in batch normalization, but there are some kind of important kind of differences. And then we have here the so-called multi-head. So the input tensor to the multi-head self-attention is really a layer normalized version of X. And we will see also here some kind of a familiar to us skip connection. This skip connection has been sort of with us since the CNN kind of days with residual kind of networks. And it is actually helping out quite a bit for the same reasons over here as well. Remember, the reasons was basically gradient flow. And so this is the point where we take an X and we produce a Z hat. And what we will do subsequently, this is our sort of contextual kind of embeddings. We will take this Z hat, at least a version of them, the Z hat. I will pass it through a layer normalizer. And we pass it through this MLP, which is the raw compute stage. And finally, we end up with the so-called X hat. All right, so what we have sort of skipped a little bit, a couple of things here. First of all, we have skipped the concept of masking. We have skipped the discussion about layer normalization. I just wanted to provide the sort of at this point, this kind of end-to-end kind of diagram and visit each one of those kind of areas that we have not treated right now. So I want to spend some time on masking. And this masking is going to be associated with a self-attention kind of mechanism. And I think it's best if we are to see this on the, if we are to see this on the side. So definitely what we would like to do is when we have, there's a typo over here with respect to a K6, but every single thing on the lower diagonal is kind of a minus infinity. When we want to decode, and let's say we are, let's say at the third token right now, and we issue a query, let's say Q3, definitely we would like to receive help when we train the network from all the tokens that precede the third position. But definitely would like to not receive any help from the tokens who are after the third position, because effectively during inference, when we estimate the probability of the next token, these tokens will not be able to give us anything because we do not know exactly what is going to be generated. So what we actually do in the self-attention kind of mechanism, we do not want to cheat during training. During training, of course, we have everything, but we definitely would not want to receive assistance in this for our representations on any future tokens. So we would like to make those attention weights 0. And one way to make this attention weight 0 is to actually, as you can see here, set these values to scores to -infinity. So when the softmax is applied, e to the -infinity is going to be 0, and finally the attention weights will end up being 0. So that's a kind of a simple way of taking care of that. That's basically what's called masking. And therefore, the full name of the sort of attention mechanism is the masked multi-head self-attention. Okay, for this reason. The other sort of approach that we would like to so the other thing we would like to do is to sort of, and I think this comes back to some kind of a dimensioning kind of exercise. Now, if you go into the multi-head kind of self-attention, you will actually see this kind of areas of layer normalization. And the layer kind of normalizer here is similar to what we have looked at earlier in terms of batch normalization, as I have said, but instead of actually doing it across the batch dimensioning, the estimation of the mean and the variance, and therefore normalization between the mean and variance, we actually are doing it across the dimensions of each token. And so we will see that very clearly in the code when we have this kind of implementation in front of us and start to map this sort of block diagram with what we see in the actual implementation. Okay, so I think this was basically the end of the discussion with respect to block diagram of the transformer, and the only thing that we have missed is this. Something is happening in the input that was not necessarily with earlier kind of architectures. And this discussion has something to do with positional encodings. So we have left we looked at masking. We postponed the discussion about layer normalization. And this discussion is a bit more elaborate done in the batch normalization video. That I have also linked below, and also in the actual implementation. So effectively, layer normalization, we will see, is a kind of a transposition of the batch normalization. And the third discussion, which I think requires some more sort of expansion here, is the so-called positional embeddings. And there are two forms of positional embeddings that I would like to sort of cover. The first one is the so-called Fourier method. First of all, we need to understand why we need positional embeddings. And the second, but if we realize that we do, the first method we'll see is this kind of Fourier method. And the other method is, I will call it the trainable embedding method. These are two different ones, and I think both of them to some degree are present. The GPT-2 implementation is more on the trainable embedding kind of method kind of side. Fourier methods has been with us in a kind of an earlier kind of architectures, but some implementations still insist on those. Okay, so what we try to do with positional embeddings and why we need it. Well, before, if you remember, in this kind of recurrent neural network kind of architectures, we are receiving some kind of tokens, one after another, and we could not form the next state, H1, before the H0 state is formed. And the same thing goes for all other states. So we have, let's say, X1 and let's say X2, X3, X4. And each kind of token here is producing a hidden state, and subsequent hidden state cannot be formed before that. So there was some kind of sequential way of forming one state from another, and we could not really. So therefore, there was no need. There was the fact that we have to sort of feed one token at a time was inherent in that kind of sort of architecture. Over here, because we are feeding this whole X tensors at the input, there isn't anything in the architecture that kind of sort of preserves that kind of order, and therefore we call this type of transformer architectures permutation invariant. So if you take this X and I permute the rows of that kind of X tensor, I will arrive in a kind of the same kind of representation at the output as I have arrived if I haven't got a permutation. But as we know, order matters. So it is kind of imperative to actually take care of that order and encode that kind of order in the architecture. And this is basically what positional embeddings are achieving. Okay, so with that said, there are kind of the first method I want to cover is this, and this equation is kind of to some degree similar between the two methods. So we have, let's say, let me call this xi, which is the input embedding into the transformer after the sort of positional embedding is incorporated. So this is basically, I'm starting from its xi, and I'm adding, which is my context-free vector, and I'm adding some Ri, which is my positional encoding vector. So this is my and this is my context-free. And we can ask the question why we are adding into the context-free vector. Are we not going to distort it by this kind of addition? As we will see, we take care of this kind of a contextual, our positional kind of encoding vectors to not have large amplitudes. That's point number one. Secondly, if we are to not add it, but to concatenate it with a context-free vector, then it probably will result into increase in the dimensionality of that x tilde vector. And this obviously will have some detrimental effects in the complexity of the transformer. So if you can get away with this kind of addition and a kind of by being careful, then I think it's the best way of accommodating that kind of information. Specifically for the Fourier method, we are going to have the encodings RIN. So this is I is the index of the token. In the context. And N is the nth element of the Ri vector. So this one will take the form of sinus of I divided by L to the power of N divided by D, or N is being even, and cosinus of I divided by N minus 1, sorry, L to the power of N minus 1 divided by D when N is odd. And if you see the plots of this kind of sort of vectors, so definitely we expect some kind of a periodic kind of relationship between the position and across the position, you expect some kind of a sinusoidal relationship. If you see those, you will see the following. So if I plot this, and what are the indices here? So over here, this is the index of the position. of the token in the context. And over here are the dimensions of the embedding positional encoding. So this is the embedding dimension. In fact, this is basically the R I, whatever I is, 8. Let's assume that we have, let's say, 8 of those positions. Let's say the dimensionality of this encoding of the position of its token has 8 dimensions. So this is RI7 ... R11. You will, and if you plot this, if you plug these kind of things, you will see that this is basically a sinusoid which is very high frequency. This is a sinusoid which is slightly kind of less frequency, and this is another sinusoid with even more and even more, sorry, even less. And so this is basically something like that you will pop up. So every sinusoid here has high frequency when it is on the first dimension, and much lower frequency when it is on the 8th dimension. And it's kind of very puzzling as to why this could actually serve as anything to do with positions. And and by the way, if you are to do that, if you are to, let's say, if you are in position, let's say 3, you draw a line, and every point that it cuts this kind of sinusoids, that's going to be the elements of your Ri vector, the R3 vector in this case. So this is your R38, this is R37, and so on and so on. It doesn't really matter. This is basically your R31. Okay. And so that doesn't really make a lot of sense as to why this construction is carrying any positioning kind of information. And I think the in kind of a Bishop's book, it's kind of very well described here why this is the case. Let's assume that I have do exactly the same exercise, but instead of doing this kind of analog frequencies, the sinusoids, I am going to do everything in the digital domain. So if I am to sort of encode, if I have, let's say, 8 digits to encode positioning kind of information, definitely I am going to start with positioning 1. Let's say if the token is position 1, my 8-digit representation is going to be 7 zeros, 1, 2, 3, 4, 5, 6, 7, and 1 at this kind of position at the end. Then position 2 will be encoded as 0, 0, 0, 0, 0, 0, 1, 0. Position 3 will be encoded as 0, 0, 0, 0, 0, 0, 1, 1, and so on and so on. So you actually can see here the last kind of digit over here. It's definitely a digit that is flipped itself every single position, right, that goes by. So it's a very high frequency change. If you see the second kind of digit from the end, this is a change which is less frequent. So it's actually double the frequency, sorry, half of the frequency of the previous kind of column. So this is a little bit less frequency. This is even less frequency. This has even less, and so on. So it kind of matches what these kind of analog versions of these positional encoding vectors are actually doing if you do it, if you look at it at a kind of a digital version of it. And so you may use that kind of sort of analogy to persuade yourself, yes, indeed, there is some kind of sort of positional information there. So what I just established here is the digital to analog analogy in positional embeddings. Okay, so with this, I think we have closed the loop, so to speak, with respect to the block diagram overall end-to-end of this kind of a transformer kind of a block that consists of multi-head self-attention elements and row compute elements. And these blocks are going to be stacked on top of each other in a much larger kind of architecture that we'll see best in an implementation, as I mentioned. And actually, what I forgot to mention here, this MLP stands for multi-layer perceptron. This multi-layer perceptron is nothing else than just a very simple dense layer, as we will have seen in the past in the dense layer architecture, except that the nonlinear units are slightly different. They're called GELUs because they have something to do with Gaussian kind of an error function. And we will see that in the implementation, and also on the website there is some kind of a plot of this kind of transfer function. These are all secondary kind of elements of the architecture. I think personally the most important element of the architecture is to understand the single and multi-head self-attention kind of mechanism and what it does effectively to form these, finally, the contextual embeddings. So I'll stop the video now, and what I will do is I'll transition now to the implementation, where we're going to map principles such as this and the concepts that we have discussed here to actual code.